Hello, my name is Julia Merwe, and my project compared the diffusion sampler and copper tube sampling techniques for the extraction and analysis of noble gases in groundwater. Noble gases are non-reactive and therefore easily diffuse across surfaces. In order to sample groundwater with its noble gases, we use copper tubes because the malleable nature of copper allows it to be clamped closed in the field and reopened in the lab for analysis. My samples were taken in Elmvale, Ontario, about a 45-minute drive northwest of Barrie, Ontario. The groundwater in Elmvale is among the purest in the world, which makes it of particular interest. The middle picture in this slide shows the copper tube sampling technique. In this method, groundwater is flushed through the copper tube for about 7 minutes, after which the clamps are tightened. First, the clamp at the outflow end is closed, and then the clamp at the inflow end. After a seal is made, the sample can be transported without the loss of water or gases. The picture on the right shows the diffusion sampler. Within the diffusion sampler, there are a series of semi-permeable membranes which allow for gas exchange to occur within the sampler. This method takes a sample of only gases, while the previous method takes a sample of the groundwater and gases. The gas-only samples from the diffusion sampler allow for easier analysis back in the lab. However, the diffusion sampler requires a much longer sampling time in the field. The letter A in the picture shows the water inflow site, and the letter B shows the outflow. Numbers 1 through 6 show the copper tubes, which are clamped closed like in the previous method. The copper tube sampling technique requires only about 20 minutes per sample in the field, while the diffusion sampler technique requires upwards of 48 hours for 6 samples. A second component of my honors project was to determine a minimum time allotment for sampling in the field using the diffusion sampler. In the advanced research complex, I was able to create a line which allowed for aliquots of gas to be taken from the sampler at any time and measured the concentration of the gas using a residual gas analyzer, or RGA. To determine at what point the sampler reached equilibrium, I compared the ratio of nitrogen to argon in both pure nitrogen gas and atmospheric gas. Using the RGA, the pure nitrogen gas had a ratio of 80 and the atmospheric gas had a ratio of 40. First, the diffusion samplers were flushed with pure nitrogen gas. Then a sample of gas from the diffusion sampler was measured with the RGA to determine the initial ratio, which should be around 80. Then atmospheric calibrated water was pumped through the diffusion samplers. About every hour, a sample of gas was taken from the diffusion sampler and measured with the RGA. This was repeated as long as necessary for the ratio of nitrogen and argon to reach 40, indicating the samplers were at equilibrium with the atmosphere calibrated water. Figure 1 shows the calibration curve for the diffusion samplers using water flow of about 1 liter per minute, which was the measured flow at one of the sites sampled in Elmvale. The sampler reached equilibrium after 300 minutes. Figure 2 shows the calibration curve for the diffusion samplers using water flow of about 0.4 liters per minute, which is a much more common flow rate of groundwater. The sample reached equilibrium after about 350 minutes. These results suggest that there is a relationship between the speed of water flow and the time for the gases to reach equilibrium within the diffusion sampler. The results suggest that faster flowing groundwater requires less time for recalibration than slower moving groundwater. This knowledge can therefore help reduce the overall amount of time required for sampling in the field using a diffusion sampler, though slower moving groundwater would require more time for sampling than faster moving groundwater. Thank you.